In this second part, we want to show that y equals f of x, which is the series that we're working with, is a solution to the differential equation x y prime minus y equals 4x squared over 1 plus 2x, for absolute value of x is less than capital R, where capital R is the radius of convergence from part A. Well, we know from part A that the radius of convergence is 1/2. And so this looks very complicated, but actually it's pretty straightforward, the ideas that are employed here. We'll just remember for a second that the function we're working with, y equals f of x, is the sum from n is equal to 2 to infinity, negative 1 to the n, 2x to the n, all over n minus 1. And if we wrote out a few terms of that, starting with n is equal to 2, we will get the first term will be positive. That'll be 2 squared x squared over 1. Second term will be negative 2 to the third x to the third over 2 plus 2 to the fourth x to the fourth over 3, etc. And it will be alternating there. So what we want now is to find the derivative of that, because we need y prime. So y prime is f prime of x, and that is simply the derivative of the term-by-term derivative. So from the x we'll bring down the 2 times 2 squared x over 1, then 3, 2 to the third x squared, in this case over 2, plus 4, 2 to the fourth x to the third over 3, etc. So that's our y prime. Next thing we want to do is multiply that by x, and we get, so xy prime would be x times f prime of x, and that is simply multiplying each term by x, 2 squared x squared over 1 minus 3 2 cubed x cubed over 2 plus 4 2 to the fourth x to the fourth over 3. So that's our x y prime. Now all we need to do is do a term-by-term subtraction. So we want to subtract from that minus y, and the y terms were 2 squared x squared over 1 minus 2 cubed x cubed over 2 plus 2 to the fourth x to the fourth over 3. From this, we just need to do a term-by-term subtraction. Notice that we have like terms all across the board here. Like terms, and like terms again. So we're going to do a term-by-term subtraction there, taking care of the negative signs as we go. And so we end up with x y prime minus y is going to equal, we have 2 square x squares over 1 minus 1 2 square x squares over 1, so we're going to be left with just 1 2 square x squares, 2 squared x squared. And then we have minus 3 2 cubed x cubes over 2, and subtract a negative, so we'll add 1 2 cubed x cubes over 2, and that'll leave us with a minus 2. x2 cube x cube over 2, and you'll see that those 2's will cancel out, and then we have 4 2 to the fourth x to the fourth over 3 minus 1 2 to the fourth x to the fourth over 3, and that leaves us with 3 2 to the fourth x to the fourth over 3. Again, the 3's cancel, and you can see that what we're ending up with here is simply 2x squared minus 2x to the third plus 2x to the fourth, etc. If we wanted to take the negative into consideration there, we could also write that as negative 2x squared plus negative 2x to the third plus negative 2x to the fourth. And what we're ending up with here is a geometric series with a is equal to 4x squared and r is equal to negative 2x. And it converges when absolute value of negative 2x is less than 1, or x between negative 1/2 and positive 1/2, which gives us the same radius of convergence as we found above. And finally, we'll just go in and put together the limit as n approaches infinity of the nth partial sum, which is a over 1 minus r, will be equal to a, which is 4x squared over 1 minus negative 2x, leaving us with 4x squared over 1 plus 2x, which is what we were trying to show in the first place there. So that'll do it for this problem. There's a lot going on in there. Again, just piece it together part by part. You can find the derivative of y. You can do a term-by-term multiplication by x to get x, y prime. Then you can do a term-by-term subtraction, assuming that you get like terms there, or there's some way to match them up. And we ended up with a geometric series that had a radius of negative 2x, and then starting value of 4x squared. We can plug that into our formula and show that it converges to that within our interval of convergence. So that does it for this problem.